The importance of creating sustainable habitats for long-term lunar colonization cannot be overstated. This extensive mission entails a multitude of obstacles that require robust and innovative technological solutions. The idea of lunar habitation, once a figment of the imagination, put forth by science fiction writers, or an audacious vision entertained by starry-eyed dreamers, has now transitioned into a genuine achievable objective that scientists and technologists globally are relentlessly pursuing. To bring this vision to reality, the primary requirement is the establishment of permanent habitats on the Moon. These habitats should surpass the scope of mere makeshift tents or temporary shelters. They need to exhibit strength, stability, and resilience to endure the severe conditions of the lunar surface for prolonged periods. For instance, they must be ready to bear the impact of lunar dust, which is sharp and abrasive, posing a serious threat to any structures and equipment. That's why it's critical to design and construct these habitats with durability in mind, to provide a haven for future lunar explorers amidst the rigorous lunar environment. The lunar surface is far from being a welcoming environment. The lunar atmosphere, a near vacuum, has pressure levels about 100 million times lower than on Earth. This absence of atmosphere results in severe temperature fluctuations, with daytime temperatures soaring as high as 127 degrees Celsius and plunging to minus 173 degrees Celsius at night. This lack of atmospheric pressure, coupled with an absent magnetic field, exposes the lunar surface to high radiation levels. The surface is also under constant assault from micrometeorites, minuscule particles of space debris hurtling at tremendous speeds. Therefore, these proposed habitats must provide a shield against numerous adversities. Constant radiation and micrometeorites jeopardize the integrity of these habitats and the well-being of their dwellers. The extreme temperatures and the vacuum conditions inject additional layers of complexity in the design and construction process of these habitats. To form such secure and safe habitats, one viable option is the employment of modular structures. These structures can be designed and assembled on Earth and subsequently transported to the Moon for installation. Taking the example of the International Space Station, ISS, its modular design allows for flexible layout changes and easy expansion or modification as needed. Additionally, a modular approach simplifies repair and maintenance, as individual modules can be replaced if damaged or outdated. The choice of materials for these habitats is a critical aspect. They must be lightweight to minimize transportation costs from Earth to the Moon and durable to withstand the harsh lunar conditions. For instance, materials like aluminum alloys or carbon fiber composites may prove beneficial due to their high strength-to-weight ratio. Therefore, the chosen materials must strike the perfect balance between weight and durability. It is essential to also reflect upon the impact of these habitats on the lunar environment. Sustainability is not just about the survivability and functionality of the habitats over the long term, but also about reducing their impact on the lunar environment. The aim should include building habitats that coexist harmoniously with their surroundings and can support life without causing harm to the lunar environment. In conclusion, the key to successful long-term lunar colonization hinges on the development of sustainable habitats. These habitats will need to be robust, modular, and constructed from materials that are both lightweight and durable. This is a formidable task considering the array of challenges that lie ahead. But with advancements in technology and the joint efforts of scientists and engineers worldwide, achieving this objective is firmly within our grasp. Modular structures, crafted from lightweight and resilient materials, present promising solutions for constructing habitable environments on the Moon. The establishment of human life on the Moon requires more than just human ambition. It calls for advanced life support systems. These are not just systems, they are lifelines contributing to the viability and longevity of human life in non-Earth environments. To truly comprehend their importance, it's essential to understand that the Moon is not a friendly habitat. Its atmosphere, or lack thereof, presents a considerable challenge in establishing human presence on the lunar surface. This is where advanced life support systems come into play, acting as a bulwark against such adversity. Let's take a look at these systems. They serve as the fundamental core to the survival and sustainability of human life beyond the confines of Earth. Not only must they be robust and reliable, but they must also be designed to operate with minimal human intervention. For example, in order to maintain a constant supply of oxygen, these systems would need to operate continuously without the need for constant or maintenance. Essentially, they need to mimic Earth's natural ecological processes to sustain human life in an otherwise inhospitable environment. One of their key functions is to recycle air. This involves capturing carbon dioxide exhaled by astronauts and converting it back into breathable oxygen, much like how trees on Earth absorb CO2 and release oxygen. This process needs to be efficient, as there's no room for error. We're not just talking about providing breathable air. It's about creating an environment suitable for human life, just like a forest does on Earth. Water recycling is another crucial function. Water, as we know, is a crucial resource for humans, but it's not readily available on the Moon. Therefore, recycling water from all possible sources, like the humidity from an astronaut's breath and sweat, is of utmost importance. This water must then be purified and made fit for consumption again. The system must also be efficient enough to cover the demand in case of an extended mission, similar to how a desert ecosystem manages its scarce water resources. Next, we have waste recycling. Human waste, rather than being seen as a problem, can be a valuable resource in such a scenario. It can be broken down and used to generate life-supporting elements such as methane, which can be used for energy production, and other nutrients vital for plant growth. Just imagine if we can turn our waste into fuel for energy and nutrients for plants, much like compost in a garden. The complexity of these systems highlights the scientific prowess and technological advancement we humans have achieved. It also underlines the challenges we face in this endeavor. It's not just about creating efficient systems, it's about devising a strategy that can make lunar habitation sustainable, not just for a few months, but for years or even decades, just like creating sustainable cities on Earth. This is where technologies such as regenerative life support systems come into the picture. These are not just life support systems, they are potential game changers. They are designed to regenerate or renew themselves automatically, thereby eliminating the need for frequent maintenance or replenishment. Moreover, they could potentially recycle 100% of human waste, an achievement that could revolutionize space travel and habitation. They could play a crucial role in maintaining a closed-loop life support ecosystem within lunar habitats, similar to the sustainable ecosystems we see in nature. In conclusion, to sustain human life on the Moon, advanced life support systems are not just essential, but they are the fundamental building blocks to the future of human space exploration. These systems must recycle air, water, and waste to minimize reliance on Earth-based resources. Technologies such as regenerative life support systems could play a crucial role in maintaining a closed-loop life support ecosystem within lunar habitats. Our survival beyond Earth may well hinge on the efficiency and effectiveness of these innovative systems, much like our survival on Earth relies on our natural resources and ecosystems. Leveraging local resources is paramount for decreasing the expenditure and intricacy of lunar habitation. This acts as the foundation of our efforts and plans, a great strategy that isn't simply tactical, but essential for survival in such a harsh setting. This is the core principle that fuels our pursuit towards inhabiting the Moon. The notion of employing local resources isn't novel. It's a doctrine that has steered our civilization from its dawn. From the primitive humans who seized stones and timber from their immediate environment to forge tools, to the contemporary metropolises that excavate and refine materials from their local vicinity to erect their infrastructure. An example being the granite quarries in Vermont being used for building New York City skyscrapers. This practice has been the key to our evolution. When it comes to lunar habitation, this doctrine acquires an even more considerable role. As we voyage deeper into the universe, the logistics of transporting vast amounts of materials from the Earth to the Moon evolves into a progressively intricate obstacle. The crucial aspect to ponder here is the expenditure of transportation. Shifting materials from Earth to cosmos demands an enormous amount of energy, which converts directly into cost. The further we voyage, the more substantial this challenge becomes. This is when the concept of in situ resource utilization, or ISRU, becomes vital. ISRU, a phrase frequently employed in cosmic exploration and habitation, is the practice of utilizing resources available in the immediate environment of a base or colony. It's a strategy that proffers multiple benefits for lunar habitation. Firstly, it significantly diminishes the weight of payloads that need to be launched from Earth, thereby reducing the cost of missions. An example of this is the prospect of using lunar soil to create bricks for building lunar habitats, instead of shipping prefabricated modules from Earth. Secondly, it cultivates self-reliance. Rather than relying on regular resupply missions from Earth, lunar colonies can employ ISRU techniques to extract, process, and utilize resources available on the Moon. This encompasses everything from water ice, which can be converted into potable water, oxygen for respiration, and hydrogen for fuel, to regolith, the lunar soil that can be employed to construct infrastructure. ISRU technologies are presently being improved and refined. For example, NASA's Lunar Resource Prospector mission is purposed at confirming the existence of water ice on the lunar poles and assessing the feasibility of extracting and utilizing it. Similarly, other ISRU technologies target extracting oxygen from lunar regolith and producing construction materials right on the Moon. Nevertheless, the execution of ISRU isn't devoid of its challenges. It involves intricate technologies and processes which need to be exhaustively tested and validated before they can be deployed on a mass scale. There is also the query of the actual availability and accessibility of resources on the Moon. While certain resources, like water ice, have been confirmed, others, such as the presence of rare minerals, are still speculative and necessitate further exploration. Despite these hurdles, the potential advantages of ISRU make it a vital part of lunar habitation plans. It is more than just a strategy. It's an imperative for the successful establishment of a self-sustaining colony on the Moon. A colony that can not only survive but prosper, paving the way for further exploration of our solar system and the universe beyond. In situ resource utilization, ISRU techniques will enable self-reliance and sustainability for lunar colonies. They are the key to unlocking our future in space, ushering us towards a new epoch of exploration and revelation. Before establishing permanent human habitats, robotic missions play a pivotal role in offering priceless data and preparing the groundwork for lunar colonization. These missions are not mere expeditions, but the significant harbingers of human arrival, acting as the trailblazers of our exploration extending beyond Earth. They are our pathfinders, our advanced scouts, making their marks on the untouched soil of celestial bodies much before human footprints etch their mark, akin to Neil Armstrong's legendary "one small step on the Moon." The strategy of deploying robotic missions before humans is an established practice. Space agencies like NASA, which developed the Mars rover Curiosity, the European Space Agency (ESA), which sent Philae to Comet 67P, and Roscosmos, which launched Luna 25 to the Moon's South Pole, have long implemented this strategic approach to ensure the safety and success of their manned missions. In the vast, inhospitable expanse of space, these robotic agents, our mechanical ambassadors, are our first line of exploration and investigation. Equipped with cutting-edge technology, these robotic missions shoulder a multitude of responsibilities. They are programmed to delve into the lunar surface, similar to the way NASA's Apollo lunar surface drill did, examining the crust, mantle, and core to garner deeper insights into the moon's geology. They carry sophisticated sensors like NASA's Lunar Reconnaissance Orbiter's Lyman Alpha mapping project that can pinpoint the presence of water ice, a resource crucial for long-term human habitation. They actively monitor the lunar radiation environment, a significant health concern for astronauts, akin to the task performed by Chang'e 4. They also map the lunar surface in detailed precision, aiding scientists in selecting the most suitable locations for future bases, like the Lunar Orbiter Laser Altimeter did. By performing these preparatory tasks, the robotic missions significantly contribute to our lunar colonization plans. The data they collect, from the detection of water ice, the radiation levels, the topography, to the geological structure, is invaluable in planning future human missions like NASA's Artemis program. Besides data collection, these robotic missions also prepare the groundwork for infrastructure. They test new technologies like Regolith that tests 3D printing with lunar regolith to build habitats comparable to NASA's Lunar Habitat Concept and other essential structures. They evaluate the feasibility of in situ resource utilization, a critical strategy for long-term lunar habitation, proven by NASA's Mars Oxygen ISRU experiment, MOXIE. By validating these technologies on the Moon, they set the stage for their use in future human missions. Moreover, the robotic missions also examine the resilience of our space communication systems. They provide a real-world platform to assess and refine our ability to command and control distant spacecraft, a fundamental requirement for human missions. They also act as communication relays, enhancing our ability to stay connected with astronauts on the Moon, like NASA's Lunar Reconnaissance Orbiter does. In essence, these robotic missions aren't just precursors. They are an indispensable part of our journey to the Moon. They are the crucial first steps we take before venturing into the unknown, the essential groundwork that ensures the safety and success of our lunar ambitions, much like Ranger 7 did by providing thousands of images of the lunar surface. These precursor missions help pinpoint optimal landing sites, evaluate environmental conditions, and mitigate risks for future human exploration. We owe it to these unsung heroes of space exploration, like Soviet Union's Luna 2, the first spacecraft to reach the Moon, to acknowledge their invaluable contribution to our quest for knowledge and our ambition to become an interplanetary species. Without them, our dreams of colonizing the Moon would remain unfulfilled dreams. Now, thanks to these robotic missions, these dreams are gradually transforming into reality. Constructing a dependable transportation infrastructure is critical for transferring crew, equipment, and supplies between Earth and the Moon. This task is intricate, necessitating a deep understanding of engineering, technology, and space sciences. Consider it this way: imagine trying to build an international airport in the middle of the ocean with no land in sight. This analogy gives a hint of the complexity of the task at hand. It involves more than just terrestrial transportation systems and includes a combination of intricate technologies, state-of-the-art materials, integrated systems, and astrophysics. The challenge is daunting. Think of it like trying to solve a Rubik's Cube blindfolded while riding a roller coaster. It needs the best brains in engineering, astrophysics, and aeronautics coming together to formulate systems that are not only trustworthy, but also efficient and sustainable. The transportation infrastructure we are discussing has the potential to kickstart a new era of space exploration, envisioning the Moon as our nearest and most achievable outpost. It's like Columbus setting sail for the New World. But in this case, the New World is the Moon, and the entire human race is on the journey of discovery. The first significant milestone in this grand vision is to establish a rock-solid connection between Earth and the Moon. Think about it like building a Golden Gate bridge from the Earth to the Moon, resistant to the harshness of outer space, including the ruthless vacuum of space, extreme temperatures, and intense radiation levels. This demands the evolution of high-tech spacecraft like nothing we've seen before, capable of ferrying crew, equipment, and supplies between our home planet and its satellite. Furthermore, there is the logistical puzzle of transporting colossal amounts of cargo with precision and efficiency. Picture a fleet of self-driving trucks traveling on a highway with no lanes, no signs, and no gravity. This requires the development of cargo transit systems that can operate seamlessly in the zero-gravity environment of space, powered by advanced propulsion systems that offer the speed of a sports car and the efficiency of an electric vehicle. The technological innovations needed to make this happen are colossal. We're talking about breakthroughs in material science akin to discovering a metal stronger yet lighter than titanium. It also involves advancements in propulsion technology, tapping into the power of nuclear or solar energy to drive spacecraft at astronomical speeds. Moreover, the communication systems between Earth and these spacecraft must be as reliable as the best military-grade technology. Picture a secure, high-speed internet connection that works flawlessly, even billions of miles away from Earth. This ensures the safety and success of each mission. Creating a sustainable transportation infrastructure involves considering the environmental impact as well. It's like trying to build a city with zero waste or pollution. This calls for the development of clean energy solutions and waste management systems that minimize the environmental footprint of space missions while maximizing efficiency and sustainability. Beyond transportation, the infrastructure also needs to cater to the various requirements of the lunar inhabitants. Think of it as building a mini-city on the Moon, complete with apartments, laboratories, gyms, and even entertainment centers, all tailored to withstand the extreme lunar conditions. The development of such an infrastructure is not just an engineering challenge, but also a diplomatic exercise. Just as the International Space Station brought together nations in the spirit of scientific cooperation, this mission requires countries to put aside political differences and work towards a common objective, fostering peace and collaboration in the name of scientific discovery and exploration. Establishing lunar orbital infrastructure could facilitate crew transfers and cargo transit between Earth and the Moon, akin to setting up a bustling spaceport in lunar orbit. This would build on the existing transportation infrastructure, creating a network of spacecraft, stations, and satellites that would facilitate efficient and safe movement between Earth and the Moon. This lunar orbital infrastructure would not only elevate our ability to explore the Moon, but also serve as a stepping stone for future missions to Mars and beyond. It's like building a launchpad to the rest of the universe, expanding our horizon beyond the Moon. Therefore, it's clear that developing reliable transportation infrastructure is a critical stepping stone for the future of space exploration. It's akin to standing at the base of Everest, staring up at the summit. It's a challenge that requires the combined efforts of scientists, engineers, policymakers, and the wider public. But with the right mindset, resources, and teamwork, there's no doubt that we will conquer this peak. Lunar colonization necessitates an unprecedented level of international collaboration and cooperation among spacefaring nations, space agencies, and commercial enterprises. On the surface, this might appear to be a straightforward assertion, but an in-depth exploration of its implications reveals its profound importance. The concept of lunar colonization, essentially the human settlement of the Moon, has been a prominent feature of human imagination and scientific discourse for centuries. It has been the subject of countless science fiction narratives, the fascination of astronomers, and the ultimate goal of space agencies globally. The realization of lunar colonization would symbolize a landmark moment in human history, a testament to our technological prowess and our relentless pursuit of knowledge. The initial element of this assertion speaks to the importance of collaboration and cooperation. Collaboration refers to the collective effort towards achieving a shared goal, while cooperation suggests a mutual mission or objective. For lunar colonization, this implies a required synergy amongst diverse spacefaring nations, space agencies, and commercial entities. They must unite their resources, exchange their expertise, and synchronize their efforts. This isn't just advantageous, it's indispensable. Spacefaring nations are those with the resources and technology to dispatch spacecraft beyond Earth's atmosphere. This includes public organizations such as NASA, ESA, Roscosmos, CNSA, ISRO, and private entities such as SpaceX, Blue Origin, Virgin Galactic, and more. Each of these organizations has its unique strengths and capabilities. For instance, NASA's extensive experience in space exploration gives it a distinct advantage, whereas SpaceX's groundbreaking development of reusable rockets offers financial and environmental benefits. Their collaboration could lead to a more efficient and effective lunar colonization process. Similarly, space agencies, governmental bodies responsible for directing and implementing activities related to space exploration, possess a treasure trove of knowledge and resources that are vital for successful lunar colonization. Their cooperation would enable the sharing of their respective expertise, the pooling of their resources, and a more concerted effort towards a shared objective. Commercial entities also represent a vital cog in the lunar colonization machine. These are businesses that undertake space-related services, such as manufacturing and launching spacecraft, offering satellite services, and promoting space tourism. They bring a fresh perspective to lunar colonization, one that is centered on profitability and sustainability. Their cooperation with spacefaring nations and space agencies ensures that lunar colonization is not only scientifically feasible but also economically viable. The forging of international partnerships is essential for ensuring peaceful and inclusive exploration of space. They serve to mitigate the risk of space exploration becoming the exclusive domain of a few powerful nations, promoting instead a collective effort involving all interested parties. In this spirit, international partnerships engender unity and cooperation, enabling nations to pool their resources and expertise for a common cause. Promoting scientific collaboration is another pivotal aspect of lunar colonization. Given that science is an international endeavor, the challenges of lunar colonization necessitate a united front from the global scientific community. Scientists from different nations could pool their knowledge, engage in joint research efforts, and collaboratively tackle complex problems. Cultural exchange is an inevitable byproduct of international partnerships. As nations and organizations cooperate, they exchange not just technical knowledge, but also their cultural practices and values. This process fosters mutual understanding and respect, thereby promoting global harmony and peace. In summary, the goal of lunar colonization is a lofty one, necessitating the involvement and commitment of the global community. It is a monumental journey that we must embark on collectively, pooling our resources, sharing our knowledge, cooperating towards a shared objective, and promoting an environment of inclusivity and peace. International partnerships also encourage peaceful exploration of space while promoting scientific collaboration and cultural exchange. Beyond merely serving as a human living place, the moon has been a spotlight of curiosity for humans, igniting our intrigue since the very first glance upward. This celestial satellite, softly illuminating the vast dark canvas of the universe, has cultivated fascination and awe. Its stark, desolate landscape and riveting silhouettes cast an enchanting spell on those who behold it, stimulating a multitude of imaginations and giving birth to countless stories, myths, and even cultural practices. Over centuries, the moon has been given various roles: a deity in ancient cultures, a muse for poets, a faithful companion to lonely hearts, and a guiding beacon providing solace in the darkest nights. However, the moon's allure isn't solely tied to its aesthetic appeal. It is also an undiscovered treasure chest brimming with potential for scientific research and space exploration. The lunar surface, adorned with unique geological formations like the Aristarchus Plateau and the Apennine Mountains, holds a wealth of knowledge just waiting to be unraveled. Studying the moon's craters such as Tycho and Copernicus, its valleys like Valles Schrotteri, its towering mountains, and the lava beds in the Sea of Tranquility can help us uncover the history of our solar system and the geological phenomena that have sculpted it. More intriguingly, the moon's environment is vastly different from Earth. The absence of an atmosphere, the extreme temperature swings between 173 degrees C at night to 127 degrees C in the daytime. The lengthy lunar day and night cycle and low gravity conditions offer a unique laboratory for scientific experiments. These unique conditions allow scientists to carry out studies that would be impossible on Earth. For example, the absence of an atmosphere means there is no wind or weather to wear away the lunar surface, thereby preserving the footprints of the Apollo astronauts and the impact craters from meteorites, providing historical snapshots into the moon's past and its relationship with Earth. The moon's close proximity to Earth also makes it an optimal platform for astronomical observations. The clear dark skies, devoid of light pollution, and the absence of atmospheric distortion allow lunar telescopes to capture sharper, clearer images of celestial bodies like distant nebulae and galaxies. Observations from the moon can provide a unique vantage point of the universe, facilitating the discovery of new celestial phenomena and expanding our understanding of the cosmos. Moreover, the moon's resources can be utilized for future space explorations. The detection of water ice in the lunar poles by NASA's Lunar Reconnaissance Orbiter and the potential for mining lunar rocks for helium-3, a potential fuel for future nuclear fusion, present opportunities for establishing a sustainable human presence on the moon. This can act as a springboard for future missions to Mars and beyond, allowing mankind to venture further into the cosmic unknown. In addition, the moon serves as a proving ground for new technologies and strategies for space exploration. The challenges posed by the lunar environment, such as the abrasive lunar dust, can stimulate innovation, leading to the development of advanced robotics like NASA's Viper rover, construction techniques for building habitats using lunar regolith, life support systems to create breathable air, and advanced communication technologies for seamless contact with Earth. These advancements can revolutionize space travel, making it safer, more efficient, and more accessible to everyone. By conducting experiments and observations in the lunar environment, scientists can push the boundaries of our understanding of the moon, Earth, and the broader universe. This ongoing lunar exploration not only satisfies our intellectual curiosity, but also fuels our dreams of venturing into the cosmos. The moon, in this sense, is not just a celestial body revolving around the Earth. It is a stepping stone, a laboratory, a source of inspiration, and a launchpad for the human race to reach for the stars. As we delve deeper into the mysteries of the universe, one of the key components for a successful long-term lunar colonization lies in mastering the techniques for lunar agriculture. It's an exhilarating thought, isn't it? A greenhouse established on the moon's surface, basking under the cold silver lunar light, fostering a plethora of plants that not merely survive, but flourish in such an unfamiliar. The significance of producing food on the moon is a matter of utmost importance. It's not just about providing nourishment, it's about promoting sustainability. The process of transporting food from Earth to the moon is not only astronomically costly, but also proves to be unsustainable in the grand scheme of things. Cultivating food on the moon would not only furnish astronauts with fresh produce, it would also contribute towards a self-sustaining habitat. mitigating our dependence on Earth. However, lunar agriculture poses its own unique challenges. The lunar soil, or regolith, is sterile, devoid of the rich nutrients present in Earth's soil. The harsh lunar environment, characterized by extreme temperatures, a scant atmosphere, and reduced levels of gravity, makes traditional farming an impossibility. But these hurdles are not insurmountable. Researchers are exploring groundbreaking solutions to make lunar agriculture a feasible reality. One such solution lies in the implementation of hydroponics and aeroponics systems. These soil-less cultivation techniques utilize a nutrient-rich solution to grow plants, making them ideal for the lunar setting. Hydroponics refers to the cultivation of plants in a water-based, nutrient-rich solution, eliminating the need for soil. This technique can be adapted for lunar agriculture by using lunar regolith as a support medium for the plants. For instance, scientists at NASA have been experimenting with hydroponic systems to grow crops like lettuce and radishes in simulated lunar conditions. Aeroponics, conversely, deals with the cultivation of plants in an air or mist environment, negating the need for soil or an aggregate medium. This method could prove to be particularly beneficial in the lunar environment, where water and nutrients can be precisely controlled and recycled, consequently reducing the need for these finite resources. NASA's research on aeroponic systems has shown promising results, with plants like spinach and strawberries thriving in such conditions. Besides furnishing food, these systems could also play an indispensable role in maintaining a habitable environment on the Moon. Plants can recycle carbon dioxide exhaled by astronauts, releasing oxygen through photosynthesis, thus maintaining a balanced atmosphere. Furthermore, they can contribute to the psychological well-being of astronauts, providing a touch of green in an otherwise desolate landscape. As we strive to transform the Moon into a second home for humanity, lunar agriculture could stand as a revolutionizing factor. Hydroponics and aeroponics could play a crucial role in this mission, turning the dream of a self-sustaining lunar colony into a tangible reality. The Moon, with its harsh conditions, compels us to innovate, pushing the boundaries of what is conceivable. And in doing so, we not only learn to adapt, but also lay the foundation for future explorations, where the stars serve not just as destinations, but as the starting points for new interstellar journeys. As we delve deeper into the prospects of lunar colonization, one of the significant challenges we must tackle is the production of energy on the Moon. Energy is the lifeblood of any civilization, and our budding lunar colony won't be an exception to this rule. Without a dependable and sustainable energy source, all other attempts, such as initiating lunar agriculture, would be rendered impossible. In our quest for viable energy sources, solar energy emerges as an obvious choice for lunar energy production. The Moon's surface is bathed in a constant and predictable amount of sunlight, making it an ideal location for solar farms. Imagine, if you will, vast expanses studded with solar panels, their surfaces gleaming under the harsh lunar light, harnessing the power of the sun, a celestial body located millions of miles away, to sustain life on the Moon. However, we must not forget that the lunar night lasts for about 14 Earth days, during which solar energy production would hit a roadblock. This, in fact, brings us to our next challenge: energy storage. Scientists are currently evaluating various solutions, including the development of advanced battery technology and thermal energy storage. Consider these systems as large-scale power banks, capable of storing the excess energy produced during the lunar day. They would dispense a steady supply of power during the long, dark lunar nights. Exploring other potential energy avenues, nuclear power stands out. The Moon is known to house reserves of helium-3, a rare isotope on Earth, which could potentially fuel nuclear fusion reactions. This form of nuclear energy is clean, safe, and highly efficient, and unlike solar power, it won't be affected by the lunar day-night cycle. However, uncovering helium-3 on the Moon and setting up nuclear fusion reactors is not a walk in the park. It's a significant technological and logistical challenge. But we've encountered and overcome lunar environment challenges before. They are not roadblocks, but exciting opportunities for innovation, continually pushing the boundaries of science and technology. So, let's paint a picture of the future of our lunar colony. It's a landscape dotted with solar panels, their metallic surfaces glowing under the cold lunar light, and perhaps even the gentle hum of a fusion reactor in the background. This reactor, even though seemingly insignificant, could be powering the dreams of a new generation of cosmic explorers. Thus, solar and nuclear energy could become the powerhouses for our lunar colonies, providing the much-needed energy to sustain life, cultivate food, conduct research, and perhaps even enable us to manufacture goods using lunar resources. In the grand scheme of colonizing the moon, energy production will be the cornerstone. It will be the lifeblood of our lunar colony, driving every aspect of lunar life, from the flicker of the lights in our habitats to the humming machines in our greenhouses. And as we harness the power of the sun and the atom on the moon, we take another stride towards becoming a multi-planetary species, expanding our horizons beyond the confines of Earth. Voiceover. As we extend our imagination into the future of lunar living, we move our attention from essential energy production to another cornerstone of any thriving settlement: communication. Forging a dependable communication system is an unequivocal necessity for successful lunar colonization. Picture this: the safety intricacies, enhanced coordination, and the psychological comfort a seamless link with our planet Earth provides. These all highlight the undeniable importance of effective communication. For a lunar colony to function seamlessly and securely, a sturdy and fail-safe communication system must be entrenched. This system isn't just a technological feat, but a lifeline, an essential tool for coordination and crisis management, and a conduit of maintaining an emotional connection with our home planet. So how do we set up such a communication system on the moon? A well-thought-out network of satellites and relay stations seems to be the answer. Picture a constellation of satellites orbiting the moon, providing a steady line of communication with Earth and enveloping the lunar colony in a network of connectivity. These satellites wouldn't be any ordinary ones. They'd be equipped with the latest in communication technologies like laser communication, which offers higher data rates and more reliable connections than traditional radio communication. Imagine the possibilities such advanced technology would open doors to. Then come the relay stations, strategically established on the lunar surface, serving as local communication nerve centers. They aren't just a receiver for signals from satellites, they're the distributors of these signals, ensuring every corner of the colony is connected. Moreover, they'd function as data centers storing, processing, and managing information from various lunar operations. But this isn't just about convenience or practicality. Communication is a basic human instinct. It forms the fabric of our relationships, the backbone of our community. Now, imagine a lunar colonist standing on the stark lunar surface, gazing up at the Earth in the sky. With a reliable communication system, they could share that extraordinary moment with their loved ones back on Earth, bridging the astronomical gap between the moon and our home planet. To sum up, satellites and relay stations could be the lifeline in lunar communication, serving as the nervous system of our lunar colony. They would be more than mere equipment. They'd be tools for coordination, crisis management, and a link to our home planet. As we progress towards becoming a multi-planetary species, we must remember that communication isn't just a practical necessity. It's an integral part of our humanity, a fundamental aspect of what makes us human.